Okay, so I'm going to start this lecture with a definition. And the definition, we want to sort of give a size of the partition. So, sorry, there's the zoom control or the Camtasia controls are in the way and are not moving. Whatever. The mesh of a partition but like something's going on down here that's just distracting me. The mesh of a partition is the maximum length of the subintervals Why is this not? Oh, restart updated or required. That's perfect. Is the maximum length of the subintervals. So in other words, the mesh of P is going to equal the maximum of all of the numbers tk minus 1 as k goes from 1 to n. Okay, so for example, if you remember back to the definition of how we did Riemann integrals in Calc 1, usually the mesh size was always going to be something like b minus a divided by the number of subintervals, b minus a over n, or that's also what we call delta x. But dealing with integrals like this, we need to have not just one mesh. We need to look in a more general situation where the subintervals are not always going to have the same length. So the mesh of a partition is the maximum of the mesh of a partition is the maximum length of the subintervals. Okay, now we're going to prove a lemma about partitions. And the lemma here is a pretty technical lemma that we're going to apply in a theorem right after this one. So it's a pretty technical lemma, but like I said, we're going to apply it. So it's something that is motivated by the next theorem. But the lemma says the following. It's basically a way to estimate what happens when you have a partition of a certain mesh size, and then you add 1 point to it. So let P be a partition P-A-R-T-I-T-I-O-N of mesh size delta. And let f be a bounded function on an interval a to b, where this is less than or equal to a. So f is a function on the interval a to b, and it's bounded. It's a bounded function, and in particular, a is the bound. Okay, and so now we're going to define a new partition. Q is going to be equal to P union one additional point. Okay, so we're just going to add one additional point to P. Then we have the following estimates. We know L of FQ minus L of FP is less than or equal to 2a delta. And we know U of FP minus U of FQ is also less than or equal to 2a delta. So let me talk a little bit about this theorem. Q is a refinement of P, so we know that L of FQ is going to be greater than L of FP. This says that this sort of gives control on how big that difference is going to be. So we know L of FQ is going to be greater than L of FP, but it can't be so much greater. Like it can't be 10 million times greater. It's controlled by this 2a delta term here. So L of FQ, if I have a refinement of, if I look at Q, or if I look at my partition P and I refine P by just adding 1 point, then if I look at L of FQ, yes, we know L of FQ is going to be greater than or equal to L of FP, but it's going to be the how much greater it is than L of FP is going to be controlled by that there. And similarly, U of FQ is going to be less than or equal to U of FP, but this says it can't be too much. It can't be too much smaller. It's just defined. In other words, it's controlled by this 2a delta here as well. Now, obviously, delta could be 45 million, and this theorem doesn't say a whole lot. But as things go in analysis, typically delta is going to be something that will be made small. And in the next theorem, delta is going to be involved. The formula for delta is going to involve epsilon, and this is going to end up being epsilon or something along those lines. Epsilon times a constant or something like that. But again, what this theorem or what this lemma is saying is that I can control the extent to which L of FQ differs from L of FP. That's what statements like this say. I know L of FQ is going to be bigger than L of FP. This allows me to control, or this gives me a control on how big that difference is going to be. Okay, so let's just prove this. I'm just going to prove the inequality for L of FP and the inequality for U of FP. In other words, I'm going to prove the top inequality. The proof for the bottom inequality is very similar. Okay, so let's just think through this. I want to compute L of FQ minus U of L of FP. Now, there's two distinct situations that could happen here. If X is already a point of the partition P, then L of FQ is exactly equal to L of FP. If I just add a point to the partition P, it doesn't change P at all. If X is equal to a point that's already in the partition P, Q is equal to P, and so this is equal to 0. Okay, so the interesting case is when I'm adding X, and X lies strictly between 2 points of the partition P. Okay, so let X be the unique integer that satisfies xk is less than X, and this is less than xk plus 1. And so the only difference between L of FQ and L of FP are going to come because when I look at L of FQ, I'm going to compute the little m for that interval and multiply it by x minus xk. Then I'm going to compute the little m for that interval and then multiply it by xk plus 1 minus x. Whereas for L of FP, I'm just going to compute little m for the interval xk to xk plus 1 and then multiply it by xk plus 1 minus xk. Okay, so if I want to know what the difference between L of FQ and L of FP are, it's all going to come down to the analysis of what's happening on this interval here. In other words, L of FQ minus L of FP is equal. Okay, so if I do the L of FQ, I'm going to get M of F over the set xk to x, should be a comma there, times x minus xk plus little m of F on the set x to xk plus 1, and then times, should be closed there, times xk plus 1 minus x, and then subtracting off the part corresponding to L of FP. This is going to be minus the minimum of F over the set xk to xk plus 1. Okay, so what I know is the following. Sorry, I need to pause this real quick, and Zoom is really being a pain, or Camtasia is being a pain. Okay, sorry about that. So now what's happening here, I know that the minimum of f over this interval, so I'm going to bring my inequality over here. So I'm going to look at the brackets first. I know that the minimum of f over the interval xk to x, that's going to be less than or equal to a, because a is the bound for the absolute value of f of x. And then I'm going to multiply this by x minus xk. Similarly, the minimum that f can be on that is going to be, in absolute value, is going to be less than or equal to a times x, or times the difference xk plus 1 minus x. And then minus, there should be an xk plus 1 minus xk. And then plus, again, I'm changing the minus to a plus. So like the absolute value of this is equal to the absolute value of this, and that's less than or equal to the absolute value of each term. And so the absolute value of this, again, is going to be less than or equal to a times xk plus 1 minus xk. But look at what's happening here. This first term, I can factor out an a, and then what I just get is xk plus 1 minus xk. So this is equal to a times xk plus 1 minus xk, and then plus this term plus a xk plus 1 minus xk. I can factor out an a again there, and then I'm just going to get a times, I'm going to get, 2a. So this is just the same term, right? So it's 2a times xk plus 1 minus xk, but xk plus 1 minus xk, that has to be less than or equal to delta, because xk and xk plus 1 are both in the partition of p, and so that's going to be less than or equal to delta. And that's exactly what I wanted to prove. And so proving the corresponding inequality for u is going to be basically the same, except the you'll have u of fp minus u of fq instead of else, but the principle will be the same. Okay, so that's it for this theorem, or this lemma. In the next theorem, we're going to apply this. We're going to apply this lemma kind of inductively. You will see it when we get to it.